start with some clarification of concepts that will enable us to understand what it is about. Soil moisture is the total amount of water, including the water vapor in an unsaturated soil. The soil moisture or soil water represent the water in land surfaces that is not in rivers, lakes, or groundwater, but resides in the pores of the soil. Soil moisture is a measure of water stored in the soil zone that is accessible to plant roots, making it a major contributing factor to plant health and crop yield. We have to know that flowers, trees, and shrubs requires moisture level between 21% and 40%, while all vegetables require soil moisture between 41% and 80%. So this condition will enable us to know what is the percentage of soil wetness or soil moisture that is required for the plant we are considering or we are observing in our study area. So those elements will vary from region and from type of crops. We have to distinguish also the gravitational water, the capillary water, and the hygroscopic water. And they are defined based on the function of the water in the soil. To know if the soil is moist, just squeeze it, and if the soil sticks together, you know that that soil is moist. That is a basic approach of identifying when you are on the field, the level of moisture of the soil. The Global Root Zone Moisture Analysis and Forecasting System, GRAPS, is produced by the ANU Center for Water and Landscape Dynamics. The model estimates the surface between 0 and 5 centimeters and the root zone between 0 and 1 meter soil moisture at a spatial resolution of 10 kilometers globally, and use the precipitation measured by the Global Precipitation Measurement, GPM, mission, and through assimilation of the soil moisture product from the Soil Moisture Active Passive mission. Kindly, you can visit those sites to have more information about it. This product is regularly updated and made available through the National Computational Infrastructure Open Access Trades Data Server. We have to thank Luigi Renzulo and Siyuan Tian. For this notebook, we will demonstrate the following step: the retrieval of surface and root zone wetness through the NCIS Trades Open Data Service and compare the soil moisture to precipitation data from ARA5. To start the analysis, we are going to run the cell in the notebook by loading the package. In loading the package, we will import the Python packages that will be useful for the analysis. And those packages are the following: the matplotlib inline, we import the data cube, that is the repository of the imagery we will going to use. We import the numpy as NP for the arithmetic or the numerical Python approach. Import Rio OX array as Rio, the X array as XR from the DE Africa tools load era 5, import load era 5. From Digital Earth Africa tools plotting, import display map, and from matplotlib import pyplot as PRT. What are the parameters we are going to use for the analysis? We are going to define the location and the time period that we are interested on. And by doing so, we define the latitude. We have to determine the latitude based on the central latitude to analyze, and the longitude based on the central longitude to analyze. We define also a buffer, that is the number of square degrees that to load around the central latitude and longitude. The time is the period for which we want to load the data for. And the output CRS will determine our coordinate reference system that the loaded data is to be reprojected to. Now, in the first cell here, we are going to define the area of interest. And our area interest here is Bartington, located in Plateau State in Nigeria. The parameters latitude are defined 9.772 and longitude 8.947. We define the time window. Soil moisture data is only available from 2015. This is an information we are providing. That is the period where the data is available from 2015 and to 2020. Anything before 2015 is not available. So we selected the time 2017 and 2020. And the output CRS is EPSG 6933. So we run this cell. And when we run the cell, we notice that here you have the number 1. That means the cell has been executed. We are now going to combine the central latitude longitude with the buffer we have defined, and we execute it. So we are familiar with this approach now. I will not spend too much time on this aspect. So it is executed. We have now to view if the coordinate and the buffer we have defined cover our interest. And by doing so, we come to display map X equal long range and Y equal lat range, and we run it. Just a minute, I'm coming. So this is our area of interest. That is Bartington. We're now going to retrieve the surface of the root zone wetness. So the surface wetness is measured relative to wetness condition recorded for a location. The root zone soil moisture index is derived from the surface relative wetness. So this function, we will going to load the soil moisture data. We define it by load soil moisture, defining the latitude, longitude, the time, the product surface. And we will use the grid by using the nearest for the resampling and those parameters that will be required for this analysis. We split the time window into years because we are considering the years. And we will execute this cell. The cell is executed. We go to the next one, that is we retrieve the soil moisture using the query parameters. Surface wetness is equal to load soil moisture. We load the soil moisture we have defined previously based on the latitude, longitude, time, and the grid using the nearest. So this one is executed, and it will enable us to retrieve this variable. We have here 2017, 2018, 2019, and 2020. By retrieving the surface soil moisture, we use the query parameters where the product is the root zone and the grid, we use the nearest. So we are interested here in the root zone. And we know that the root zone has been defined between 0 and 1 meter. So we have this variable here for 2017, 2018, 2019, and 2020. We now need to plot the surface and root zone wetness over the time, because those elements are determinant in the behavior of the plant, because we know based on what is outside, that is in the air surface above the ground, the plant is subject to wind, sun, and other atmospheric elements that will now have an impact on the evapotranspiration. And based on those temperature and weather condition, the plant will absorb or will evaporate much more water. And if the soil is not wet enough, it has an effect on its phenology. We are going now to resample the data to get the monthly mean. By defining surface wetness is equal to surface wetness, we resample it by using the time monthly and having the mean. And we come back here, root zone, we do the same for the root zone. We define the root zone wetness, resampling using the months, and for each month we have the mean is executed. The surface wetness is given by the latitude, longitude, and we are going to represent them by defining the figure size, and we label it as surface. The same for the root zone, we define it and we label it as root zone. That's what we have here, the figure we have here. And the legend here gives you the surface in blue and the root zone in orange. I will reduce it a little bit so it will enable us to have a global view of the period we are considering. And you notice that from 2017, okay, from 2017, there is a variation of the wetness, both in surface and at the root zone. We started from January 2017 and we ended our analysis in January 2020. We start with the surface. Surface is where you have the water received from precipitation. So as during the dry season, you notice that the surface is dry, the value are lower. But as the rainy season is established from April towards May, we notice that we have an increase of the wetness of the surface. And it's continue following the trend of the rain pattern during that year. So when it reached towards the maximum, towards July, August, there is the trend to the reduction of precipitation leading to the end of the rainy season. You see a decrease of the wetness of the surface up to December, January of 2018. But what we notice is also you have a little shift between the wetness of the surface and the wetness of the root zone. What does it mean? The root zone is considered between 0 and 1 meter. During the rainy season, there is a time of wetness, and when the water touches the surface, it has to infiltrate or percolate towards the down part of the soil and making those areas wet. And as they are not exposed to the sun, the evaporation is related, or the absorption of that water is dependent on the temperature in the outside and the evaporation and transpiration of the plant. But still, the water contains much more wetness, the soil contains much more wetness. That's why during the dry season, you see that the wetness is a little bit higher than the surface wetness. And as the rain is taking place, you see also that the wetness increase and follow the trend of the precipitation during the rainy season. So as the rain is decreasing, the soil still contains its wetness, enabling the plant to sustain its growth and the maturation of the product considered. So that is what we are noticing for the year 2018 and 2019 up to 2020. So you see that there is a shift between surface wetness and root zone wetness. So as far the root zone is wet, the plant has water to absorb and enable the photosynthesis and the phenology to take place. I will go back to the following. So now we will save our results as a CSV file, and we convert the surface wetness and the root zone wetness data set to data frame. So we write the surface wetness DF is equal to surface wetness dot relative wetness dot mean lat lon. To data frame, we define the lat lon and we plot it. And when we have done such, the table that we have as CSV give us as titled surface relative wetness and the root zone saltwater index. So you have the time and the wetness, relative wetness, and the water soil index root zone. So you have this value, and you notice that from 31st January 2017, the wetness, it was equal to 0.06, and the root zone soil water, it was equal to 0.08. That means the root zone was wetter than the surface. In 31st of May 2017, it was in surface 0.45 and in the root zone 0.27. That indicate the infiltration and percolation of the water inside the soil through the pore and the capillarity of the soil. We are going now to save this our result as a CSV, and we name it as soil moisture DF to CSV result soil moisture, and we define the time and the starting time and the end time. That is time 0 and time 1. Now we are going to compare the soil moisture to the precipitation using the data from ERA 5. This, the first cell will load the precipitation parameters, precipitation amount, 1 hour accumulation from ERA 5. Depending on the size of the query, this step can take some minutes to complete. So as the query, the size is high, the time of processing will be longer. So we load the data precipitation from the ERA 5. Variable precipitation is equal to precipitation amount 1 hour accumulation, and we run that that one. We plot the soil moisture precipitation, and we will have, sorry. So the last one is now to compare the precipitation and the cell. And we find out that you will have that correlation we have mentioned earlier about the precipitation as much is precipitating as the soil is getting wet in the root zone. Just a minute to complete this process and you will have the result. So pending the time the system is doing the processing, that was the last part of this presentation. If there is any question, I'm at your service. Thank you very much, Knut.